it's kind of like social media kind of fucked up our attention spans, and I find it kind of difficult lately reading and writing. So maybe it's something with me specifically, but I really kind of struggle with reading and writing lately. True that, like a lot of people can confirm, right? So I don't know what's up with that. Is that the social media, or maybe it's actually the results of COVID? Like, this is something that I said jokingly, I think on Twitter or somewhere else, but I mean, it's kind of a half of a joke, right? So as far as I know, like COVID was also attacking neural cells, right? So, like, is it possible that one of the side effects of COVID was that it actually gave you brain damage, right? So, and we collectively, as a humanity, got a brain damage, like some sort of a permanent brain damage, right? And since we got the brain damage, we can't really see that. And since we collectively got brain damage, like we can't even identify the brain damage in each other. Right, so I know that it sounds like a very convenient argument that is impossible to disprove or anything, but just think about that, right? What if the humanity just got collectively nerfed? Like, and all of a sudden, all of this hype around artificial intelligence starts to make sense, right? So if we didn't lose all of the IQ points we lost due to the COVID brain damage, we wouldn't think that artificial intelligence of today is smart. We literally think it is smart because we're brain damaged. So this is my theory. This is my conspiracy theory, right? So there was no advancement in AI at all. We just all collectively got a brain damage, and because of the brain damage, it looks like AI is smarter than us. You know what I'm talking about? This is my hypothesis. This is my theory. So I know, yeah. So the points, the name of the points on my channel are actually fitting to this rant. It's actually fitting to this rant. COVID brain damage, exactly. So I think we collectively got the brain damage from COVID, and that's the like all of the we see today is the result of that. Implying humanity was intelligent before, true. That's my first mistake. All right. So yeah, we've got a B compiler in here, chat. We've got a B compiler, but unfortunately, it doesn't have that many examples, right? So there's not that many things to demonstrate how this compiler works. So we have a couple of things, and I think all of the things in here are literally hello worlds. Right, so we have a hello world in here, which just prints hello character by character. I also recently off-screen implemented support for printf, right? So you can now use printf. You can't really use printf with numbers because we don't support, functions with more than one argument. I mean, because we didn't need that before, right? So as soon as we need that, I can implement that. Right, so and I think we have another example here, which prints E a couple of times, but I mean, it's a very convenient example for testing mathematical operations, right? So we have multiplication, subtraction, addition, and stuff like that. So it's just like all of these examples are kind of lame, right? So, and since I plan to actually port this language to many different platforms, I think I need to have some substance, like what exactly are we porting? Right. So let's actually go ahead and implement maybe a couple of simple examples that we can then use to port this language to different platforms like ARM, MIPS, WASM, right? So we have a lot of different platforms to port on. So what kind of examples should we implement, right? So something simple, something that we can implement within like 2 hours of the session and stuff like that. Something that is not hello world. I think like Fibonacci numbers, right? Let's actually start with Fibonacci numbers. So how developing the Fibonacci numbers would look like. So let me maybe set the mode to simpc. And by the way, I'm using C. Actually, not even C, but C++ in inline comments, which don't exist in B. But the reason why I'm using that is because I just like took a stock C lexer, and basically from the lexical point of view, my B language looks like C. But since there is not that many differences between C and B, like lexically, it kind of works out, right? So after I finish working with my B compiler, I think I'm gonna iron out all of the differences between the B and C lexer, right? But for now, I'm just using the lexer of C. So Valeni, thank you so much for tier 1. Thank you. With the message Tsodin around, yeah, it's a really funny emote. Thank you so much. So I hope I didn't miss anyone. And also Pawn Theory, thank you so much for tier 1 with the message 43 years of quality Tsodin. Thank you. Really glad to hear that. All right, so let's actually introduce the entry points. And what's fun is that I kind of like bcompiler. I kind of like the fact that you don't have to provide the return value, neither do you have to provide any types or anything. In fact, there's no types in B. There's like only one type, which is word, right? So, so whatever the size of the word of the machine you're programming on, in case of PDP, I think it was 16-bit word, right? So in our case, it's going to be 64-bit. So this is B64 specifically. So, and let's actually allocate a bunch of variables in here, right? So it's going to be A, B, and C. And again, I don't have to specify any of their types. I only have to specify the storage class, which is auto. And auto storage class basically means that the variable is allocated on the stack, which means that once the execution goes out of the scope, all of these variables are going to be deallocated, right? So then let's actually define first two Fibonacci numbers, so A and B, so 0 and 1, and we'll have to introduce while loops. So right now compiler doesn't really support while loops, right? So but what we need to maybe compute them up until million, right? Something like that. So, and after that, I need to print this specific number like this. And by the way, I need to declare this thing as an external symbol, otherwise I won't be able to use printf, right? So you kind of have to forward declare this entire thing. So after that, I need to find the sum between A and B, and let's not make the mistake I did last time, right? So A is equal to B, B is equal to C. Did I make any mistakes in here? I think I'm computing Fibonacci numbers correctly, right? Well, I mean, to be fair, on the previous stream I made that mistake because I was a little bit tired, right? So, that's basically what I want to be able to support. There's a little bit of a limitation in here, is that we can only right now define one variable at a time. A proper B compiler would allow me to do something like this. And maybe this is something worth implementing on today's stream as well, right? So maybe this is something worth implementing on this stream as well. So we need to implement this. We support this, we support this. We do not support while loops, so we'll have to implement that. So we also don't support, less operation. We don't support comparison, but we have all the necessary infrastructure for binary operations for bnops. So we should be able to actually add that relatively easy. And we do not support function calls with more than one argument, right? So the maximum arity right now is 1, but again, it's very easy to add. So I guess that's everything we need to implement to actually be able to compile this example. Right, so not that much, honestly, not that much. So let's actually go ahead and try to maybe compile this entire thing. I'm gonna like recompile the entire compiler, right? So the entire compiler is recompiled. So, and now let's actually supply this example. So it's gonna be phi b, and as you can see, it cannot basically define several variables at once, right? So because after definition of the variables, what it instantly expects is semicolon. Right, so it doesn't expect comma or anything like that. Let's go ahead and add support for that. Sounds good, Tamaguchi, let's fucking go. So src, so here is the B compiler. It is written in Crust. For those who doesn't know what is Crust, it's basically an unsafe variant of Rust. And we're using it just for fun, right? So because we want to have fun. So we can find more information about this variant of Rust in here. And maybe it makes sense for me to put it in here in the description. So compiler work. So here is the Crust, and also as another sort of reference in here, I'm going to put the link to the compiler, to the B compiler, for anyone who's interested. All right, so and because it's an unsafe variant of Crust, expect a lot of weird shit like row pointers, for instance. As you can see, we're literally using row pointers. Each individual function is unsafe in here. Everything is absolutely unsafe. This is basically an ugly C. C was already pretty ugly before that, but we made it even uglier. But to be fair, even with the ugly syntax, I think Crust adds a little bit of a nice things, in my opinion. For example, slices are pretty good. So slices help a lot, I think. Also enumerations, right? So enumeration is actually quite powerful, even in Crust. So yeah, it's an all right language. It's an all right language. So we'll get some subs. Thank you so much, KT64_T with a message. Another month of recreational programming. Indeed, indeed, absolutely true. Oh yeah, yeah, that's kind of funny. So there's like a double pointers in here, especially if like so it's a pointer to pointer. Yeah, and this is how you define all that stuff. It's how you define all that stuff. So Yesu, where do we define the variables? Does anybody know? So first we need to compile function body, right? So we need to compile the function body, and here is a bunch of autos. Yeah, there we go. So here's the auto keyword. As soon as we encounter auto keyword, we even have a to-do for that. Look at that. So this is the literally to-do that I'm implementing right now. So we expect an ID, right? We expect an ID. Then we take the name of this ID and we basically declare a new variable, right? So and variables have different storage and stuff like that. We have a special function that, given the name and its storage, it just declares the variable in the scope. That's basically what it does. And we emit intermediate representation instruction that allocates the variable and so on and so forth. And we explicitly expect he attack, he protect, most importantly, he expect. And we expect a semicolon, right? So we expect a semicolon. So don't forget a semicolon, chat. Don't forget a semicolon, otherwise you're gonna waste 3 hours. So, and essentially what we need to do in here is basically do that in a loop somehow, right? So in some sort of a loop. So we expect an ID, all right. But interestingly, right, so here's the loop, expect an ID, declare the variable, and so on and so forth. And here, basically what we need to do, we just need to make a decision, right? So we need to get the next token. I don't remember what is the function for getting it. Okay, so it's stb selector get. All right, so we get in the next token. Right, and then here we need to switch upon like different situation, right? So I'm not sure how easy it is to use switch in here, so I'm going to use if. If lex, I think token is equal to semicolon as silong, as shlong, right? So this is what you have to do. That's basically the end of the declarations, right? So there's nothing much we can do in here. So I'm going to break out of this specific loop. Maybe I can even specify the, the label, right? So because loops can actually have labels. So how should I call it? Maybe vars, right? So we can call it vars. And I'm saying that I'm breaking out of vars. If it is comma, right, so if it is specifically comma, we just continue, defining the variables. We simply continue defining the variables. But if it is not comma, we have to say that this is an expected character, right? So here it has to be comma, right? And if it's a comma, we just continue. Maybe it makes sense to explicitly say that we continue in here, right? So we don't really have to do anything, right? So if we just do anything, it will just continue looping. But then it's kind of unclear, like what's the point of this specific condition. So I'm going to explicitly say continue, right? So if it's a semicolon, I'm breaking out of that loop. If it is a comma, I'm continuing and sort of explicitly saying what's going to happen in here. And otherwise, we encountered an unknown, token. So we need to report an error. I don't remember how to report errors. So let me actually look up how it is done in this specific function. So it's somewhere here. So it calls to function expect collects, and it is using diagnostic macro, which reports the location and stuff like that, and so on and so forth. So this is probably what we're going to be using in here, right? So I'm going to just put it in here. We're going to report the diagnostic, and on top of that, we'll have to return false. So, but I don't quite remember. Does it return Boolean? Yeah, okay. So it does return Boolean in here. And this is how we report errors in here. All right, that's pretty cool. So we supply the Lexa, the diagnostic needs a Lexa, then the input path, and then where the character is located, right? So that makes sense. And in here, we just have to say expected, maybe either semicolon or comma. So what's interesting is that we do not have, we have a function for actually displaying human readable names of the tokens. It's called display token kind temp. And I think I need to follow the convention that this specific function sets up. Right, so I want to say expect that or that. And in these specific cases, I'm going to explicitly call display token. Right, so if the way I report you know, the names of the token is going to change, it's going to change here as well. So through this function, I'm sort of standardizing the way I'm reporting different token names to the user. I think it does make sense. So and in here, I'm going to say expected either this as clonk, right? So it has to be clonk as clonk. So we have, like, Rust actually has a type called clonk. Send it, well, Clonk probably knows that, but send it to Clonk, right? So just let him know that Rust actually has a type with his name. It's called Clonk. So, and also a semicolon in here. All right. So expected that or that, but got actually that. So this is what we have to say in here. Honestly, you guys don't know who's a Clonk? So it's a pretty epic streamer. C colon, I think C colon, I forgot his name. L colon Q, L colon Q, right? So I'm pretty sure it is some sort of a command in Vim. I'm pretty sure. I'm actually quite convinced that, yeah, so this is basically him. And I'm gonna put him in here in the chat. Wait a second, I think Twitch has some sort of like a shout out thingy. So shout out L colon Q. There we go. Did it do the shout out for the streamer? Right, so did it do the shout out for the streamer? Okay, so follow him. He's a pretty cool streamer. Okay, so I don't know how all of that works because I don't use Twitch. I actually don't watch Twitch. Like almost at all. I watch Jonathan Blow sometimes, but I watch him on YouTube. There is an official archive channel that archives all of his Twitch streams, and I just watch him through that. Right. So for me, it's kind of difficult to watch Twitch because it's kind of a garbage website, right? So it's so janky and slow. It's just like I can't use it. One way to use it is maybe through MPV, and sometimes I do that, but generally I just don't watch it. So anyways, there we go. So this is basically what we have to do. Honestly, what I'm doing is already done by expect collects function. What it does, right, so it takes the token that you expect and compares it with the token in Alexa. And if it's not the token that you expect, it will tell you that. But it only works with one token. There's no way to tell it, okay, expect either that or that or that or that. Right, so there's no way to tell it expect several of them. Unless we can try to make it to do so, right? So, because as far as I know, you can have, what is it called? Slices. We can try to do that. So unsafe if expect collects, right? Several collects. So here we accept this entire thing, and then we accept the input path. Input path is kind of important because we're using it in reporting. And then I want to accept several collects, right? So I suppose I can pass it as a slice like this. And in here I can say to do. Right, so this thing is not implemented. I'm not going to even specify it like that. Right, so and the question is how you even use this entire thing. I need to go back to where I were, right, somewhere here. So if I try to do something like this, I specify the Lexa and I specify the input, but then can I just say, okay, I expect several of these things like that. I expect either this or I expect this. Will that work? Especially considering that we're accepting a pointer slice, not a reference slice. Right, so there's different two kinds of slices, the one that are accepted by a reference and the ones that are accepted by a pointer. So here we're accepting it by a pointer. Will that work? That's a very interesting question. Maybe it will, right? So, and if it will, that is very freaking cool, honestly. That is actually very freaking cool. So in that case, I'll be able to do something like this, right? So I get the token, I expect one of these two lexers, then if it's not that, I can basically return false, right? And this entire thing essentially becomes unreachable, right? So I can say unreachable like this. So yeah, that's much better. I kind of like it better. So let's try to compile that, right? So I'm really curious if it's going to work or not. And if it will work, so that will prove that Crust has some advantages over pure C, right? So because I thought that if I strip off all of the safety from Rust, it's going to be basically as an inconvenient as C, but that will actually demonstrate to you that, yeah, so there's some conveniences because you can't really do this kind of stuff in C, can you? Well, I mean, there is a compound literals that allow you to pass an array, but you can't pass a size of the array along with this thing syntactically nicely. You know what I'm saying? Like syntactically nicely, you can't really inline it like that. With this kind of stuff, if it works, we're passing not only the data of the array, but also the size of the array. Right. So we also pass in the size of the array, so it's kind of cool. So people suggested macro. We could have used macro for variadics in here, but I think writing a macro for that is going to be even more anal than it is already. So I don't really want to go with a macro route in here, unfortunately. Sorry about that. So yeah, let's give it a try. Let's actually go through the compilation errors and see if it's going to give us anything. Look at that. Okay, so I probably have to dereference all of this stuff. So let's actually dereference all of these things. And it's already saying warnings and stuff. So expectation, yeah, so I'm sorry about that. So what's else in here? Cannot apply unary operator to this thing. Is that because I never returned? Look at that. I never returned a Boolean. So that's the reason. And yeah, that worked. Look at that. So you can actually literally do that. And it's totally fine. And I think it doesn't really leak any memory, right? Because where is that array allocated? I think it is allocated on the stack. And then once you go out of this thing, it's just deallocated. Unless we try to hold onto the pointer that points to this array, I think we're totally fine in here. Yeah, it is stacked. So this is nice. This is something that I can't easily do in C. I can't really do that, but it's not going to be nice. So that is definitely an advantage over C, like in here. That's definitely an advantage. I kind of like that. All right, so let's actually see how we can implement that. So essentially what we need to do, we need to iterate the classes, right? So I'm going to go and iterate I in 0 classes len, because the Rust slices are weird like that. And if, let's say, we have to dereference this entire thing, classes I, not equal to L token, hola. If it's not equal to that, we need to report an error. This is where we're going to be reporting an error, right? So let me actually copy this stuff in here, and I'm going to return false. So, and if we iterated through all of the tokens and we encountered, well, I mean, yeah, that's the interesting thing. If it is equal to any of the token that we expect in here, we can safely return true right away. And if we, after iterating all the tokens, didn't encounter the one that we expected, this is where we have to report this and that stuff. So I think that's how I'm going to go about that. And in here, obviously, we return false. So we need to now report a list, right? So we need to iterate through all of these things. And basically say, okay, expected either that, or that, or that, or that, or that, but got whatever we got. So, and because we have a variable amount of tokens in here, we have to construct a pretty long string in here. So that sounds like a job for a string buffer. Right, so we have a string builder. It's called string builder, and it comes from the knob. I'm actually using knob in this compiler, believe it or not, in Rust. Like I'm literally binding a lot of functions from knob, and they're super fucking convenient. And one of them is sbappend, which allows me to printf into this string builder. It's insanely convenient. It's insanely convenient. Okay, so let's actually create this kind of thing. So string builder, and I'm not sure, do I want to free it or do something about it? Right, so let's actually not free it for now. So this one is going to be mutable, obviously. And I probably want to make it like zeroed, right? So it's allocated on the stack, and then it's zeroed out. So, and in here, we want to iterate all of the tokens in here one more time. And they're going to be SB appending their name. SB appending their name. Is that a good idea to even do it like that? So because we allocating a little bit of a name on a temporary allocate, and then we're allocating it in a heap, but maybe that's fine, right? I shouldn't worry about it too much. So in here, we're gonna print something like this. All right, so display. And we take the classes, we dereference the classes, and we put them like that. So it's going to obviously concatenate all of them like this, but what we can do, we can basically separate them with spaces, right? So maybe another thing we can do in here, if I is greater than 0, then basically append a comma space in here. What's funny is that we don't really need append for this kind of thing, but I think we can just append sister. And that should be enough. And by the way, this entire thing should be obviously a C string. By the way, so remember how we discussed like how to conveniently use string literals in Rust? Because these C string literals that Rust itself provides are not even convenient for what they're designed for, right? So all of these motherflippers, they have type like this. Right, I don't really know how you spell it, but I think you spell it like this. And this is the type that is not passable through FFI. It is literally not passable through FFI. Even if you have this kind of literal, you still have to do SPTR, and I suspect Rust developers did that intentionally. So several people actually told me off screen that there is an easy way to create a macro that would allow you to do something like this, right? So we explored how to do this macro, but we couldn't find like a very convenient way to do that. So, and somebody pointed out at a very interesting macro in Rust, which is called concat, which may help us with this kind of thing. So it concatenates string at compile time, right? You can concatenate strings at compile time in Rust, right? So it's called... yeah, I think it's this one. Yeah, literally, it's this one. It's a string concatenation, but at compile time, and not only string. Look at that, not only string. So it works with any literals, so like integer literals, characters, or booleans and stuff like that. It can concatenate anything. Can concatenate. Okay, so which means we can actually, I think, create a pretty cool macro rules. Let's call it C. Right, so and in here we're going to be accepting the literal, right? So I'm going to call it L, and it's a literal. And what we can do in here is concat L and 0. Right, so we automatically like prepending 0 in there, which means we're not using built-in C literals. We're not using that. And after that, we can just do SPTR for this entire thing. But what's interesting is that this is not a C literal anymore. This is a Rust literal. And Rust literals have a pointers to U8. They're unsigned bytes. But C literals are actually signed bytes. And I think on top of that, what you have to do, you have to actually cast this thing to const i8 for that to work. But let's actually confirm that. Let's actually confirm that. I'm not going to do that. But that's one way to do that, right? Actually, several people told me that you can probably do it like that. So let's give it a try. I haven't tried it yet. So I think it's a pretty good opportunity to give it a try. Right, so in that way, it's a little bit of a syntactical craft, but it's way better than doing like at pointer, right? So if you have something like this, which is better, this or this? like, it's clear that this is at least shorter. It's uglier, right? So it's uglier, but at least it's shorter than this thing, right? Why I8? Does it make any sense? It's a good question, because character, I think in C character is signed specifically. It is specifically signed, and maybe to distinguish on a type level different string literals, like a Rust string and C strings. I don't really know, but that's how it works. All right. So let me see. Has anyone subscribed so far? Nobody subscribed. Okay, that's cool. All right, so we can try to do that, and we're appending this entire thing. Man, I really dislike that I can't do it in a single line unless I do this ugly thing. But yeah, anyway, whatever. Okay, so we're collecting this entire stuff, and then we can finally say expected something like this, right? So expected SB items, right? SB items, but got whatever we got. So it would be nice to maybe for the last character in here to say like or, right? So because just because you list them, it's not obvious that you mean or in here. But anyway, let's actually make it work first, and we'll see how it goes. On top of that, I think it makes sense to append null at the end of this entire thing, but I'm not sure if we do have append null in here. But we can always do something like da append this and just append 0 in here, so that should be enough. So, and after that, I feel like it makes sense to actually free this entire thing, right? It makes sense to free this entire thing. So display token allocates memory in a temporary allocator, so that means you don't have to worry about freeing it. But this one, it allocates on the heap, so it kind of makes sense to actually free it in here. Anyway, so this is basically a rough outline of the thing that I want to do. All right, so let's actually go to the compilation errors and see if we can fix anything in here. So yeah, we have to, yes, specify the input. I put underscore in here. So anything else we have in here? Append sister. We don't have append sister in nob.rest, really? Okay, so let's actually bring it from nob. I mean, I don't mind. So here is the third party, nob.h, append sister. And fuck, this one is, all right. Append many. It's basically an append many. I think relatively recently, I created append many, but I created it so it actually accepts a slice. So that's a little bit painful. That's a little bit painful. It accepts a slice, but we can probably create a slice out of this thing. I don't freaking know. Can we? Can we create a slice out of this stuff? I think we can. Wait a second. Who said we can't? We can. Because what we can do da append many, and string builder, if I'm not mistaken, string builder is just an alias to an array. It's a dynamic array. And then we can do this thing. We can take that one and basically as bytes, right? Is as bytes a thing in here? Is as bytes a thing in here? I'm pretty sure it is, and it's part of the like string and slice and stuff like that. And it's going to return U8, which is a little bit annoying, right? Considering that in here, string builder, it's a C char, which is actually I8. Anyways, so yeah. But maybe I can recast this entire thing to a freaking... We'll see. Let's actually let the compiler tell us like what exactly we have to do in here. Let's let the compiler tell us. All right, so what do we have in here? And of course, right, of course, it's just like, yeah. So one thing we can do, we can then say as, well, we can't really say that as pointer, but maybe you can, as ptr. Can you do that as ptr? Yeah, and it's not even the pointer to the slice. It's not even the pointer to the slice, motherfucker. I'm thinking, okay, can I just do C? And this thing doesn't have as bytes. Right, so this one doesn't have as bytes. It has, well, it has bytes, which gives you probably some sort of an iterator over bytes. It's an iterator over bytes, and on top of that, it's a nightly. Can anybody fucking tell me what's wrong with restitutions? Like, are they okay? Did somebody hurt them or something? It's just like, this is not healthy. Like, this API is not healthy. It's just like, it's very unhealthy. Like, I'm genuinely concerned. Are you guys okay? It's just like, is everything fine? Or like, what the fuck am I? Two bytes. Okay. And it's U8, but I want I8. 2 bytes with null. I don't fucking know, man. To string. 2 bytes. And it's U8, but I want it to have signed bytes into C string. Just transmute. I'm thinking about transmuting it. And ironically, I'm thinking about transmuting it. Okay. So, okay, so, and okay, here, as you can see, it expects I8, and we already confirmed that, right? So I const as const I8, like that, and that works. Right, okay, so it's like literally the only reason I'm using overkill append of is because Rust being annoying. If Rust wasn't being that annoying, like I wouldn't have to do that. Okay, so this macro is actually kind of useful, right? So I think this is the macro that we should use from now on, instead of just like this thing, which also means we don't really need Rust 2021. So the only reason why we use an addition of Rust 2021 is because we wanted to have this sort of macro in here. But we just realized that it's not usable for us, so we might as well just like, you know, downgrade the edition. I think that's one thing we can do. So yeah, to be honest, we usually use overkill printf instead of fputs most of the time. That's true. That is true. So maybe that's fine. And it looks all right, actually. It doesn't look really that bad. So I have a special module in here called Crust. This is a module that facilitates Crust-style programming. Right, I want to eventually grow this module into something pluggable. Essentially, if you want to start programming in Crust, you would download this module, just use it in your project, and there you go. You have everything to start programming in this specific style. But the thing is that I need to figure out what this style means. Right. So essentially, I just imposed the limitations on this style in the form of rules. But I don't really know what this rules implies, because they obviously pose some sort of challenges. So that means you need to come up with the ways to overcome those challenges. And the ways you overcome these challenges is what defines the Crust style, right? For example, we just discovered that this macro like really well like overcomes the limitation of using Rust literals, Rust string literals with C really well. So that defines a Crust style. Right, so that means it makes sense for me to add this thing to this module now. Right, so it also comes with Crust entry points. It defines an entry point for you. It defines a nice panic handler for you, so you can actually use things like panic to do an unreachable in Crust, because they all will redirect to this specific panic handler. Right, so all of that comes with that specific module, right? So the idea is that eventually to develop into something that you can plug into your project, and there we go, you're programming in Crust more or less convenient. libcore, it's basically Crust core, right? So it defines a bunch of things for you, like printfs and stuff like that. So anyway, yeah, that's basically what we have in here. And by the way, since we have a nice macro for C literals, I think we could remove automatic S pointer for the printf macro. But unfortunately, printf macro is actually used in so many places. That means I'll go into the huge rabbit hole of refactoring everything. So I'm not going to be using it right now. Right. So I'm going to do that off screen. But since we have this like little macro, like we don't have to do this kind of like nice things for you. But anyways, okay, so let's actually continue. So all of that seems to be compiling, and what do we have in here? So see, yeah. So since I moved it into a separate module, what I have to do, I have to export this specific macro, like in this specific style, right? So macro export, and now I should be able to use it. So look at that, chat, look at that, chat. So we have a special expect function that expects several macros for you. I want to see how does it work. So I want to go to my Fibonacci.b and let's put maybe exclamation mark in here, right? So because we obviously parse a variable and then we expect either comma or semicolon, you see exclamation mark and it's going to error, and I just want to see what kind of error message there will be there. So I'm going to do B, and what do we have? Expected, comma, or semicolon, but got this one. But as you can see, we can't see that this is OR. We kind of have to put OR between all of them. Right, so let me see. So I'm going to go to here. So where is expect? We can literally just do something like OR. Like this. I'm going to rebuild the whole thing and I'm going to rerun it. Right, so expected that or that, but got that. But what if you have many of them? What if you have many of them? So let's actually see. Expect classes. Right, so maybe I'm going to do class ID, maybe class dig string or something like that. And let's see how the error message is going to look like. Right, so as you can see, expected identifier or string literal or comma or semicolon, but got this. Is putting or in between each individual option in here a good idea? It looks kind of stupid. I think it would be nice if or was only the last one. Right. Yeah, so you need to put it only in the last one. Right, so we put it here and it actually jumps in here. It's really nice. It's really nice. And I think, like, again, obsessing over diagnostics in compiler is really important because, as Jonathan Blow said, a diagnostic is the interface to your compiler, right? It is literally interface to your compiler. Your input is the source code and the output is either the final executable or diagnostic. And it's literally the UI. It's UI of the compiler. So it's very important. It's very important. So now, how are we going to be doing all of that? How are we going to be doing all of that? If I, first of all, I is greater than 0, right? It's first of all has to be greater than 0. And if I is, I don't know, the last one, yeah, if I is the last one, but how do we know it's the last one? If I plus 1 is equal to the length, right, to the length, might as well, just in case, greater or equal, only then you kind of do that. Otherwise you just do that, right? You just do that if something in between, right? So that's basically the condition. It's a little bit complicated, but I think it's worth it. Yeah, so expected identifier, string literal, comma, or semicolon, but got this thing. So let's test some other things. For example, when you have only 2 options, right? So what if you have only 2 options, like in our case? In our case, it's going to be 2 options. So in this specific case, it will say or, which is exactly what we expect. But what if you have 1 option? What should you have? 1 option, in that case, you only have that one, which means that expect classes is just a general case of expect class, and which means you can implement expect class in terms of this more general function. So that's very nice. So we can do just something like this, right? So, and instead of classes, we can just literally do class. Look at that. So, and it doesn't break any of the existing code. So now it's literally the same thing. It's literally the same thing, which is nice. So it's a rather convenient way to just like expecting things. Okay, expected that or that. That's cool. Let's go back to this entire thing. So we're expecting specifically this thing. So there's a little bit of a problem with adding more tokens in here, right? So you have to modify this kind of stuff in two places, right? So I want to now expect another token. So I have to add it in here and then add it in here. But since I'm testing the unreachable case, I will get reminded about this specific place at runtime. Not compile time, but at least at runtime. Right, so essentially when I encounter something that I added in here but didn't handle in here, I'll hit unreachable. So that's why unreachable macros are so freaking important in any language, not Rust. It's always important to crash at an unreachable place, because one day, for whatever reason, it may become reachable, and it becoming reachable is a bug that you want to fix. So just put assert in there or something, right? So in the old languages, it's usually assert. In the modern languages, there's literally unreachable thingy, some keyword or some macro or something like that, right? So it's a very common practice. It's a flavor of assert. Flavor of assert. Okay. So let me try to do that. And what do we have? An expected token identifier. I suppose it worked. All right, so as you can see, now it crashes in here, so that means it went past this, and now it tries to compile that. So let's actually do the following thing. I'm going to comment out this entire thing, right, like so, and see if it's going to compile. And it in fact compiles. We can now actually use a target IR, right? It should create the intermediate representation for the Fibonacci. Does it have a intermediate representation for? Yeah, there we go. It does have it, but it created it in such a weird way, in all honesty. So yeah. All right. And as you can see, it allocated 3 of them. Right. So for each individual variable, it allocated it like that, which makes me think maybe we can collapse them together into a single thing, or do I care? Might as well. So, but to do that, first of all, I have to move emitting an instruction outside of this entire loop, right? So I'm emitting it outside, and now I have to count how many variables are allocated in here, right? So let's maybe create some sort of a count, and every time I declare a variable, I just increment that count, and I'm just put this count in here, right? So that means the instruction is emitted only once. And yeah, so basically collapsing all of these allocations and stuff like that. So let's try to do that one more time. Okay, so let me see, and there we go. So alloc 3. So we defined 3 variables and they just got allocated like that. So yeah, we finally implemented an ability to allocate variables in a single line, several variables in a single line. Look at that. Isn't that cool? I think that's pretty cool. So because at the beginning of the stream, the only way to allocate 3 variables was like this, right? And we literally were spending, how much time we spent? An hour to make it allocate like this, right? So this is what we were working on, by the way, if anyone is interested, right? So and this is how much code it required. Well, but I mean, we refactored a little bit. We also created a very cool way to expect certain tokens, and also very cool diagnostic mechanism. And on top of that, we also added a cool C macro. So just saying. So it was not just like, you know, stalling or wasting time. We also improved the code. People are pointing out at simp-C. I thought like everyone who watches me knows what is a simp-C. Like, you guys don't know what is a simp-C. I can show you, right? So simp-C is a mode for C programming that I developed myself. It's my custom mode for Emacs for programming in C. You can actually find it in here. It's called simp-C mode, and it stands for Simple C mode for Emacs. Simple C mode for Emacs. I can explain to you what exactly this mode is about if you're interested. So simp-C mode for Emacs, because whatever comes with Emacs is too slow I just speed it up. This mode does not try to be as featureful as C mode, C++ mode, CC mode, etc. Instead, we're trying to implement a bare minimal syntax highlighting and indentation to maintain high performance on big files with long lines. The goal is to be able to comfortably browse and modify the following files. For example, ImGUI header file. The problem with ImGUI header file is that it has enormous lines, huge ass fucking lines. We can download this entire thing. All right, so it's gonna be something like that. Let's fucking go. Right, so I'm gonna open it up and it works fine. I can work with this entire thing. Right, but then I switch to the official C mode of Emacs. Right, and I try to just scroll and I think, well, I mean, I think they improved the performance in the recent Emacs, so it actually performs really well with long lines. Okay, so they improved the performance of long lines. I can give them that. I can give them that. But there are way worse cases in here. For example, there is an amalgamate of SQLite 3.c. So essentially, what the SQLite developers did, they took the entirety of the source code of SQLite and they concatenated it into a single file, into a single translation unit, right? And sometimes I wanted to modify this amalgamate, and I couldn't even open it in Emacs. Right, it's a 7.5 megabyte text file. It's the single file that is the entirety of the source code of SQLite. Right, so let's actually see. And right, so the size is 222,876 lines of code. Right, so that's what it is. So I'm in SimC mode. I'm using SimC mode, and as you can see, it's pretty fast. But then if I switch to C mode, first of all, it hung for a second. Now it finally switched, and I'm trying to browse this entire thing. I go to the end of the line, and it hung, and only then it went to the end of the line. Right? I'm gonna go to the beginning of the line. It's fine. Going back to the end of the line, it's totally fine. It actually loaded it. Right? But if you open it for the first time, you go to the end of the file. Okay, so I suppose it cached it. By the way, maybe they improved the performance. Wait a second, I'm on a new laptop. That probably explains it. So, yeah, I'm on a new laptop that also uses SSD and stuff like that. So that actually drives my point to home even more, right? So if you are using a shadier platform, you just a shadier computer, you just develop a better software, right? So as you can see, I bought a better laptop and now I don't see a difference between a shady mode and non-shady mode. So yeah, should have not used actually this new laptop. Should switch back to my old laptop. Oh, when you reopened, yeah, I'm sorry, I'm an idiot. Okay, so hanging. So let's actually jump to the end of the file. This is how much time it took to jump to the end of the file. So it's still shady. Okay, so I forgot to switch the mode. So several seconds, honestly, several seconds. And if I use SimC mode, I'm in SimC mode. I'm trying to jump to the end of the file. Instantaneous. So the problem is not Emacs. The problem is the implementation of the Emacs mode. It just does too much crap that is not needed, at least for me. Right. I don't really need all of that crap that it does. All I need is a little bit of a syntax highlighting and a little bit of an indentation. And I implemented that and it works perfectly. I can modify 7.5 megabyte files easily, very conveniently in Emacs. So that's basically SimC mode, and I just use it for everything that is related to C from now on. Right, so that's basically the lore behind this mode, behind the SimC. I don't use the built-in Emacs mode like at all. So where's my description? Did I put, yeah, so let's actually put this thing in the description for anyone who's interested. So it added this stupid tab stuff. But anyways, okay, so BRS, I think the time has come to do a committee and potentially a push. So here's the track file. So maybe makes sense to get rid of all of this stuff and obviously of ImGUI and SQLite. Do I want to commit this kind of thing? I think I want to commit this kind of thing. All right. So wait a second. I think I had to do for the feature that I'm implementing right now. I didn't remove to do, look at that. So I need to remove to do now because it's already implemented. We also have variables with external storage, and if I remember correctly, according to the spec, B allows you to specify, to sort of like forward declare several functions, right? You should be able to do things like, for example, put char and strlen, right? So you should be allowed to do these kind of things, but we don't do that, right? So, but we're going to implement that separately, and I think I want to focus on it right now. I want to focus only on the automatic variables right now. And to be fair, it's literally the same code, right? So it's just like here is extern. And I'm doing almost the same thing that I do in auto, except that I'm using a different storage class for the variable that I'm declaring. It's pretty much the same code. It's pretty much the same code. And in fact, I could have just said, okay, if it's extern or auto, use the same code, but just like use a different storage in here. And I'm going to do that a little bit later. I don't think it's important right now. Right. Okay, so we get some subs. Thank you so much in Lois for which prime the message 12 months goes. Coraner, thank you so much for your run with the message. Kampala, I hardly know her. Okay. Very funny. Very funny. Okay, so let's commit everything we have in here. So where's the to-do? Support multiple auto declarations. And that's literally what I did. And I'm going to push that right into the repo. Okay, so that's pretty cool. My friend, pretty cool. What's going to be the next thing we need to support? If we uncomment this entire stuff, it will probably try to compile this thing. Right, it sees while, and it doesn't understand what is while. But to be fair, I would probably start with trying to compile this expression, right? Because it's the easiest to implement. So I'm going to take this entire expression and maybe assign it to C, right? Just to see what's going on. And you can do that because there's no types in B. There's only one type, which is word, which means if I do something like this, it just means that I assign in either 0 or 1, 64-bit, to this specific variable. Right. Oh yeah, so you need to put parentheses in here as well. But anyway, thank you so much. It's besides the point. It's just like a syntactical stuff. All right, so expected. There we go. So it doesn't know what is less. It doesn't know what is less. How we are compiling different expressions. Let's actually see. When we are compiling the body, so here's the compile function body, we are expecting either extern or auto, right? So we'll already pass that. Then we expect an ID, right? So we get an ID and we encounter equals, and then we have compile expression. So here is the most important function for us. So this is where all of that's happening. Oh yeah, so it leaks a little bit of temporary variables. So we can look into that a little bit later. Okay, so we do compilation of the binary expressions depending on their precedence and stuff like that. So we're doing this precedence climbing thing. So how is it called? Prat parser? I don't quite remember. So there was a little bit of a discussion about prat parsing when Jonathan Blow did a stream about that. I think we're doing that. Right, so essentially we're starting with expression with the lowest precedence, and we're going down. Brat parser, very funny, right? And we're going down, so we're starting with plus or minus, right? And then we're going down to multiplication, and then we're going down to primary expressions. So we're going like down, starting from the highest precedence and to the lower precedence. So the question is, less like the comparison operations, they have lower precedence than plus and minus probably, right? So first we do primary expressions, which are literals and expressions in parentheses. Then we do multiplication division. Then we do plus minus. Then we do comparison. Obviously, I missed a bunch of operations, but they're not implemented anyway, so it doesn't really matter. So because of that, when we compile expression, we should actually start not from plus or minus, but from comparison, right? So this is what we have to start with. And obviously, instead of like having copy-pasted functions like that, which are literally copy-pasted, right, so duplicate code, we should have a single one that passes around the current precedence. The current precedence. But right now, I don't want to spend time compressing this code because it's easier for me to copy-paste that code, right? So it's easier to copy-paste that code. So, okay. What's the value of this to piss you off? That's priceless. Okay, so let me see how we're gonna be approaching this entire thing. I think we need to just do the following. We need to introduce a new binob. We need to introduce a new binob. So we have a plus, minus, multiply. Let's introduce less. Right, so we're introducing this new binob less. Let's go to the compilation errors. So as we introduce that stuff, we now, it asks us to describe how you even compile that less thing. Like, how do you even compile? So for now, do I want to spend time describing how to compile it for different platforms? So I might as well just, you know, do something like this. To do, we'll just like use to do. I'm gonna go through all of these places. Here is what? Here is what? It's a JavaScript func body. All right, so should be relatively easy because in here, binob less, I can try to do sb append. You know what? I'm not really sure, right? So because if I do less, does it automatically get converted to 1 or 0 or anything like that? So for now, I'm going to put to do here as well, right? So because I'm not really sure. What else do we have in here? And here is binob for just the intermediate representation. Okay, so for the intermediate representation, I think I'm going to implement the generation for the left instruction. Right, so I'm going to do that. Oh, by the way, this gives me a pretty cool opportunity to use the new macro that we got in here. Look at that. Use a new macro. That's pretty cool. So that's actually a pretty cool way to solve it, right? So it's additional parentheses. Wait a second, do you even need additional parentheses in here? It looks like you do need them. Damn, maybe you don't? Look at that. So I put a space in here and Emacs still kind of highlights it properly. Huh. Is that a valid way to call a macro, chat? Because Emacs says it is, but we don't know for sure. Maybe Emacs is lying. So let's actually see. Right, so, no. Okay, so I have to put parentheses. Is there any nice way to call these kind of things? This would have worked in D, as far as I know. This would have worked in D, but it doesn't work in here. Okay, so yeah, expected this one, but got, you know, less or equal. So compile expression. Here it is. So we need to introduce a new kind of function for the comparison. Compile less expression, right? So we're going to be compiling the less expression, and this thing is not implemented yet. Right, so, and here is the less expression, like this. So obviously it's going to complain about all of these unused variables. I wish maybe I could just say allow unused on this whole thing. Can I freaking do that? I think I'm pretty sure I can do that. Yeah, so warn, and specifically for this function, allow unused variables. So you shut the fuck up. Okay. Not yet implemented, right? So as you can see, try to like compile this entire thing and it failed. Okay, so we need to repeat this entire schema of trying to parse left-hand side and the right-hand side. So I'm going to copy paste this entire piece of code and just use it as a template for what I'm trying to do in here. So we compile in less expression, but the higher precedence than the less expression, right, by 1 is not multiply, it's actually plus or minus expression, and this is what we're trying to parse in here. Okay, that's pretty cool. So we're saving the point because we're actually rolling back the, what is it called, the Lexa. So here's to add more binops of the same precedence require modification in 3 places. Yeah, that's true. It's just like we're going to fix that eventually. So, and in here specifically, we're expecting less separation, right? So we're expecting only less separation. So here, what do? We allocate a new temporary variable, right? So that's what we're doing, allocating new temporary variable, because we need to store the result of the comparison somewhere, right? And while we do in fact see less separation in here, right? While less separation is still going, we keep parsing the expressions in here. So the next one has to be plus or minus expression. Then we have a binop instruction, and binop in here, okay, this one is interesting, from token. We're constructing a new binop from token, and where is the function responsible for that? Here it is, and I didn't put anything in here. All right, so what I have to do in here, I have to say less, and this is a binop less, right? So we construct a new binop in here, and here's the autovar. All right, so then we repeat this. Okay, so this is done. Right, so we created a new precedence. Again, we should not copy-paste this huge ass function for each individual precedence. What we have to do, we have to have one single recursive function which increments the precedence every time it tries to parse the sub-expression. But that also requires to maintain a table of current precedence list of operands. Current precedence list of operands, so we can actually use that list of operands to use in here or in here as we parse and munching on sub-expressions. Right, but again, that requires a pretty heavy refactoring that I don't really want to do right now. Right, I may do it later, right, or maybe even off screen. We'll see. We'll see how it goes. We'll see how it goes. And compiles. The whole thing actually compiles. I think we'll literally just edit support for comparison in here. I'm pretty sure about that. And what are we doing? We're generating intermediate representation. Okay, that's fine. So if I take a look at the fib IR, where is the just fib? Okay, so we compare it with the original code in here. So where's the original code? So we expect external. Here's the external printf. Then we allocate three variables. Assign 0 and 1 to A and B. Assigning 0 and 1 to variable 1 and variable 2. Makes sense. Then we allocate another variable. We're probably allocating a temporary variable where we're going to be storing the result of this entire thing. And as you can see, we're applying binop less. I don't remember for. What is for? Oh. It's an index. Oh. Yeah, so I completely forgot. Yeah, we're assigning to the temporary variable. So this is the index of the temporary variable. So we're comparing variable 1, which is A, and it is in fact variable 1, with the literal 1 million, which is true. We're assigning to a temporary variable, then we assign the variable to 3 in here, right? So it's a little bit overkill, right? Too many temporary variables, but that's totally fine, right? So we can optimize that, all of that later. In any case, we managed to compile it to intermediate representation. But this is just an intermediate representation. We need to turn it into the assembly, right? So x86-64 assembly. And to do that, let's go ahead and maybe remove the target IR, so it uses the default target, which is x86-64, right? And as you can see, it panicked because we tried to, generate the less instruction that just doesn't exist, right? So it simply does not exist. So how are we going to be doing all of that stuff? This is very interesting. Right, so we have a left-hand side and right-hand side, which are arguments and stuff like that. X69 for 20. Ahaha, funny yoke. So we can probably use something like cmovge or something like that. But I've already been streaming for 1 hour and I ran out of liquid and I'm a little bit tired, chat. You know what that means, chat? You know what that means? You know what that means. That means we need to make a small break, and after the break we're going to implement the degeneration for the less binop of intermediate representation of our compile. We're back. So let's go ahead and try to maybe generate some assembly. So the thing about binops is that in binops you have LHS and RHS, left-hand side and right-hand side. So for the left-hand side, we already kind of Yeah, we already generated stuff, right? So we moved left-hand side to racks already. We already moved it to racks. So the only thing that is left is to compare it to whatever we have in RHS. The thing is that LHS and RHS, they have type of argument. So this is a special kind of type in here, which is called argument. And argument basically tells you where you get the value of the word, whether you get it from the local stack variable, whether you have it as is, which is literal, or is it located in a data offset. The data offset is actually rather interesting. So the compiler, as of right now, I didn't really stream that, but this is something that I implemented off screen. So if you take a look at what kind of assembly it generates, for example, for hello world with printf, you will notice that it has a data section. And this is the section where it stores the string literals, right? It stores it in string literals. And essentially data offset is an offset from the beginning of the section data, right? And usually that's sort of like a value is generated by string literals, right? It's emitted by string literals. And essentially you can have a comparison with either, you know, a variable on a stack or with something on the data section. That may happen, right? So because the language doesn't really forbid you to do that because it doesn't have any types. It doesn't distinguish between numbers and strings. Everything is a number for it. And as far as I know, the string literal just has a value of its address in the data section, right? So that's basically what it is. And how can we do any comparisons? I suppose we can just use CMP, right? So just to set the flags of the CPU to the appropriate state. That's one of the things we can do. Just use CMP. So bin op, like I lost the place where all of that is located. So here it is. Okay, so that's pretty cool. That is a pretty cool. And let's just do the match with RHS. So here's the RHS. Let me try to compile it so it will tell me that I need to add all of these things as what are they called? Matches. Man, this compiler doesn't make it easy to copy paste the stuff that you need to add in here. Alright, so in here we probably have to do something like this. So this is going to be that. Yep, why are you doing it like that? Yeah, there we go. So this is an index. This is a value of the literal, and this is an offset. So in case of this thing, what effectively we want to do? We want to compare this entire stuff. We want to do CMP, right? So we're comparing. What exactly are we comparing? We're comparing left-hand side, which is currently located in racks, because up front we moved left-hand side into racks, right? Just in case. So left-hand side is already moved into racks. But now we're comparing racks to a thing on the stack, and it is located at RBP minus the index, and the index, it's very important, it has to be multiplied by 8, right? So because the size of the word is actually 8 bytes. So it gives us that. On top of that, what that does is essentially just sets all of the appropriate flags and stuff like that. We need to now get the value of the flag and maybe move it somewhere. So we need to move it somewhere, and here is the index. So this is basically where we have to store the result, right? So this is where we have to store the result. What's the easiest way to do that? I suppose we could utilize some sort of instruction like conditional move. cmove, it has to be like less, right? So can I do cmove less? Yeah, so it's a less than, or I don't remember, is cmove L? It's just cmove L. Does it exist? Yeah, so cmove L just exists. Cmove L, and so it actually can accept you know, addresses and stuff like that. But the problem is here is that we need to store it into a local variable, right? We need to store it into a local variable, and I'm pretty sure we won't be able to do something like this, unfortunately, right? So this is what we're kind of expected to do in here. So this is multiplication, and we're saving it into this thing. So we do the comparison, and we're moving 1 into here, and obviously we want to do something like quad. This is not going to work for sure. So I don't really remember what's the best way to do this kind of thing, right? But I mean, I just need something that works, right? So I just need something that works. And here is the problem. So we have index. Don't we have? I think I know what is going on. I feel like what we have to do, we have to move this thing completely outside. So now we're accessing the index that is the destination index into which we're storing the whole thing, right? Into which we're storing the whole thing. For this one, we can say that this thing is not implemented, right? So this thing is not implemented, and this thing is not implemented as well. All right. So, and obviously I forgot the new line in here, and this one is the index multiplied by 8, and so on and so forth. Okay, so I don't really like how it looks like, so I'm gonna put maybe a comma in here. Does it make sense to maybe put a semicolon in here? Right, so anyways, let's try to compile this entire thing and see what it's going to say. It says things, and I forgot to prefix this entire thing with arg. Obviously, this is what I forgot. Anything else? What else do we want? SB append th. Forgot th chat. And there's another th. And anything else? Offset. Okay, so we're not using any of that shit. Anything else? Panic. Ooh, we're comparing to the literal. Of course. So why was implementing this shit if we're comparing to the literal? Obviously, in B, where the right hand side is the literal. So I just wasted time. Well, I mean, I didn't waste time because we'll need that eventually at some point, but not right now. Not right now. Okay, so this is LD, and we can literally just put a value in there. So there will be a problem in the future because... Nah, there will be no problem. So I thought that maybe you can't really move any size of the literal, but I think move and comparison works like that, so that should be fine. Okay, this is what I was talking about. Invalid operand. You can't do cmove L literal into memory. You can't do that. But we can theoretically actually basically move. I think you have to move this value into a register. So essentially we can move like 1 into RBX, and then this kind of thing. This kind of thing. Still didn't work. That probably means that what we have to do is something like this, right? And only then, might as well just clean our BX up front. Yeah, so we setting it to 0. Then we conditionally moving 1 into it if, you know, the comparison, you know, worked. And then we're moving the value of RBX into here. Will that work? Okay. So cmove L needs both of these things registers. Right, not really both, it's like a register or memory. You can't work with immediate values. Right, so you, I mean, it's not that big of a deal, but I mean, I can do something like RCX1. That's probably what it wants, right? So yeah, we're probably going to be doing setcc, right? So, but I just want to make something working for now. Yeah, so thank you so much, Angel Caro. Like, I do remember that this is the things you have to do, but I first want to make it work, right? So then we can work on a different instruction. Yeah. Okay, so that seems to be working. I'm very sure you can just put simulate with cmove. I don't remember how to do that. All right, so let me see what we have. So I have saved compilation buffer accidentally. Okay, so now if I take a look at the example Fibonacci assembly, what do we have in here? Right, so we have this kind of thing. We moved RBX8, compared to this one, compared these two things, and so on and so forth. That's pretty cool. So I would like to maybe see the result of this entire stuff. All right, can I maybe put char C? And obviously it will probably print 1. Right, so let's actually put char in here. And let's try to compile the whole thing like that. It does compile. And after that, let's do example fib. And we get this, which is, I think this is 0. I'm pretty sure this is a straight up 0 and not what I envision it to be, which it's supposed to be 1, right? It's supposed to be 1, I'm pretty sure. So we probably want to add something in here. I want to add this one, but we don't have characters. Like you literally can't do that. An expected token character literal, we can't do that. So we can take the ASCII code of 0. Does anybody remember the ASCII code of 0? So man ASCII code of 0. So where are the zeros? It's 48. I'm sure it's 48, right? So it is in fact 48. So let me see. Boom. And it is 0, but it's not supposed to be 0. So something is already wrong. I wonder what exactly. So we probably like failed something in here. It's a lowercase a. What are you talking about? Everything works exactly. So let me see. Where is the source code? Where is the location where we had the source code? I need to look at the diff to find the place where I was working on the generation. Where is the generation code? Here it is. Okay. I think I know what is going on, right? I think I know what is going on. And essentially, so this is 0 RCX. I do CMP. I quite understand. So I'm comparing Rex, which is the left-hand side, with LD. And okay, so I have RBX, which is initially 0, and RCX equal to 1. And I'm moving RCX into RBX only if this thing is less, which I mean, that means the CMP worked exactly as it needs to be. And only then I'm moving that final value of RBX to here. So something is wrong in here. Also, can we try to maybe assign 1,000,001 to A, so that will become false? Will it change anything? It literally didn't change anything. Zor reset status compare. Fuck, that makes sense. All right, so that means we have to do that here. Yeah. Okay, this is 0. And now if I bring that stuff back, okay, and that works. Okay, so that's pretty cool. So I completely forgot that you have to, like, it resets all of that stuff. Well, at least we have it, right? So at least we have it. It feels like a, you know, high-level programming language, even though it's not a real programming language. Right, it's actually kind of dumb. It doesn't even have an AST, which makes it feel like it's not even real programming language. But I mean, it feels like C. So fake it until you make it, I guess. That's one. This is basically the case of faking it until making it. Okay. So yeah. So let's actually take a look at setCC. Set byte on condition. So what kind of things we have? Set L. All right, and you have to either supply R or memory, right? And it's just 1 byte, I presume. So sets the destination operand to 0 or 1 depending on the setting of the status flag. Okay, so that's probably what we want in here. That is probably what we want in here. And it also accepts the memory, but M8. What is M8? Do I understand correctly that it's basically pointer to 1 byte, right? It only sets byte. It doesn't set like a 64-bit. So you what mate? It's freaking damn. So yeah, it's a pointer to 8 bits. Yeah. So we have to be careful in here. I suppose we can still do XOR. We do RBX, XOR RBX, and then in here we can do set L. Yeah, set L RBX, but it's not really. It has to be lower. It's BL, right? So if I put RBX, by the way, in here, if I put RBX, it's not going to compile properly at all, right? So because its operand size is incorrect. BX is also not going to work because it's 16 bits. It has to be BL, right? And we zeroing it out. So the rest of the bytes of this register are going to be 0, right? So that's basically what we're doing here. This is going to compile, right? It's not going to work, but it's going to compile. So and after that, we have to move RBX to the final destination here, right? And I guess it's not that, yeah, so it's pretty much the same amount of instruction. I think we cut down on 1 instruction, right? So we used to have 2 instructions here, 2 in here. Yeah, it's pretty much the same amount of instruction, like, but maybe it's faster, right? So because we're directly like working with this thing. Would be also kind of cool if we could just put this thing directly like that, but I can't really guarantee that this variable is actually 0. That's the thing. Like I can't guarantee that. So because of that, I think it's better to do that through a register, right? Know what I mean? Like I can't really guarantee. Like I can't put like the address directly. So it's better to do that through the register. And the register that we know is zeroed out. So this is 1. That is true. So then I'm gonna go here, put 1, 2, 3, 1, 2, 3, but 1, and this is false. All right. One more time. True. So yeah, thank you so much for reminding me about setcc. Thank you. So, and by the way, maybe it also makes sense to kind of put that into references because this is what we're using throughout of the development. So I think it's kind of important. Okay, so we have a less operation. Look at that. We have a less operation. So let's do a committee. So none of that stuff is needed. So let's remove that. Maybe I should git ignore it. Add support for less binop. Boom. We don't really have a support for JavaScript target, but I mean, whatever. JavaScript target, I probably will remove it at some point, right? So it was only for testing. Okay, cool. We advanced the development a little bit. Now we can try to compile loop, right? So we need while loops. And the last thing that we'll need is printfing. I don't know why. How difficult would it be to implement while loop? It's just like a bunch of. We'll need to introduce a new instruction in here, conditional and unconditional jump, because on a level of assembly, chat, this is very important. While loop is 2 jumps, one conditional and another one unconditional. So essentially, the first jump is conditional and it is at the beginning, which checks the condition and conditionally jumps over the body of the loop. And another one that is unconditional is at the end of while loop, and it's unconditionally always jumps to the beginning to the while. That's the entirety of while loop. 2 new instructions, and you just like strategically place them like in these places. So that's what you're doing here. Strategically placing these things. Right, so let's go ahead and try to do that. So as of right now, if I try to compile this entire thing, is it going to work? Yeah, so it doesn't understand this kind of thing. So the way we parse this entire stuff, we are looking specifically for this sort of instruction. Well, by the way, can I use a new macro in here, chat? I kind of like the new macro. I think it's kind of cool. It's kind of neat. It's better than whatever Rust developers came up with, right? So it's much better macro in my opinion, much better macro. All right, so that seems to be compiled. Look at that. That's so neat. Look at that. Nah, this is not neat. This is neater, right? This is neater. So B keywords and yeah. So I'm looking specifically for auto, right? So where is the auto? So here's the auto. All right, and here's the extern. And essentially, these keywords constitute the start of the statement. And essentially, while is one of such keywords, right? So it constitutes the new statement in here. The new statement, like so. Right, and it's going to be while. And in here, we can do something like to do while loop support. Like this. So let's try to compile that. There we go. Not yet implemented. While loop support. So that's basically what it is. Cool. Now we know that after the while keyword, we have an expression, and not only expression, a primary expression, because it's wrapped in parentheses. Right, it is wrapped in parentheses. Nah, not really sure. Yeah, so we have to explicitly expect parentheses. Okay, so after while loop, we explicitly expect open parent as clonk, and then close parent. So this is basically what we expect in here. Right. So that looks good. In here, we expect an expression. We expect an expression, clonk, yes. So let's go ahead and compile an expression. So this is a compile function body, and we have a special function that compiles an expression. Look at that. So it needs Alexa and input path and variables. We do have all of that stuff. We do in fact have all of that stuff. In fact, I feel like I need to combine all of these things into the compilation context so I don't have to pass it around like field by field, right? Field by field. By the way, here, if I understand correctly, this returns Boolean, which is kind of interesting. So I suppose compile func body doesn't return anything, but we're doing these things for a Boolean, so I'm not quite sure. If let none, if this entire thing returned, yeah, we have to be a little bit careful. We accept the argument, and through the argument, we get where that condition is stored, right? And if we got none instead, that means the error somewhere in the compilation process of the expression happened. We have to return false in here right away. So, but here we have to do something with the expression. Yeah, we have to do something with the expression. And we have to check it, right? So we have to, yeah, this is where we have to apply the conditional operation, the conditional operatione. But, so here's the thing. We need to save the current state of function body, right? What this entire recursive process do, we have a huge function actually, which is the compile expression, compile function body, and so on and so forth. We have a lot of these things. And what it is effectively doing, right? What is effectively doing, it's populating an array called function body. And it's an array of operations, basically instructions of assembly, right? That's what it does. And once we call compile expression in here, that means func body, right? So at this specific place, right? At this specific place is going to have less instructions, and then after this operation, after it was successful, it will have more operations, more instructions, right? So here you have one set of instructions. Compile expression, as it was compiling, was appending new instructions into the function body, and you have basically all of the instructions to evaluate this expression. What's interesting is that if you take the size of this thing, right? If you have the size of this thing, and maybe save it somewhere, I don't know, let's call it like a begin, and compare it with the size after you compiled expressions, you know exactly how many instructions compile expression has added. In fact, you can now use begin index as the place where you can jump around. For example, once you finish compiling the entire while loop, at the end in here, you can say, okay, now at the end, always jump to the index begin in here that you saved, right? Because after all of that stuff, we generated the entirety of the code for the while loop, and now we know where we have to jump back to actually organize the loop. So that's how it works, right? So when you are compiling control flow instructions, what you're effectively doing, you're calling different functions that generate instructions, and you strategically remembering different places in the code, so then you can stitch all of that together and organize a while loop or for loop or if else construction or switch case and so on and so forth. That's how you do the compilation. Make sense? Right, so that's basically what it all boils down to. Right, you have this array, you append it to this array, and as you append, you're also remembering different places. Sometimes you even have to go back to fill the address where you have to jump because it's not known yet. Right, so it's a lot of fun. Right, so if you never developed your own compiler, this particular part of the compilation is really fun. So you're using relative jumps. Maybe we have to use relative jumps in here. That would have been actually kind of nice, I think. We may try to do that, or maybe we can use absolute jumps. Yeah, so we'll get some subs. Thank you so much, Lily Anatia, for tier 1. Thank you, thank you, thank you. Right, so I think I missed a couple of subs. Develop Land, I don't remember if I acknowledged you. Thank you so much with the message. Thanks again for all the fun and knowledge I gained. I don't remember this message, so you're welcome. You're welcome. Okay. So here we save in the begin, and I think it's kind of important to, right, so to remember this entire thing. After we did all of that, we have to, we have to emit a new instruction. We have to emit a new instruction that does the comparison. All right, so not really comparison, but does the conditional jump. Does the conditional jump. I don't think you need to remember the position when you have an AST. No, you still have to remember the position. At least I don't see how to not remember a position, honestly. So because what we're doing right now is not that different from having an AST. It's just like when you, like the thing about parsing is that parsing is traversing an AST. Parsing by itself, the process of parsing is already a traversing an AST. It's just like you're caching your traversal so you can traverse it again if you need to. Right. So AST is only needed if you plan to traverse one more time. If you are traversing only once, there's no reason to build an AST because like you're not going to be traversing another one. Right, so it's just like it doesn't make any sense. You have AST, but only expressions for arg. It's honestly a stretch to make that statement. This is a stretch. It's literally an enumeration. It's like saying, oh, I have linked lists. That means I'm operating on trees. My linked list is a tree. Well, okay, sure. Technically it is correct, but come on, seriously? Anyway. Anyways, so let me continue doing this kind of thing. Degenerated tree. So we need to add a new operation in here. So where's the enumeration operation? Yeah, so let's introduce maybe jump, right? Where we have to specify an address, right? And I'm not sure if it's going to be relative or absolute address, but it's going to be some sort of an address. And jump if, right? So this is where you're jumping, and So jumping in here also requires a condition, and that condition has to be an argument, right? So this has to be an argument. And what's funny is that what we want to do is we want to jump outside of the while loop, right, when the condition is false. I don't really want to generate additional instructions or anything like that. What I want to do, maybe, I want to actually have something like jump if not, right? So I'm going to be doing jump if not, and I'm going to be just using this specific argument. Maybe I'm going to call it argument so it's a little bit nicer in Rust. And just generate the following instructions. So in num op, right, so jump if not. So the address, I'm not really sure, right? So I don't really know where to jump because I have to jump to the end of the body because I haven't generated that body yet. So I think I'm going to set it to 0, but arg is going to stay like this. So, and now I need to emit an instruction. So di append, so it's a function body, right? So I have to do di append func body, and this is where we have this kind of thing. Funnily enough, right, so as I finish generating the body, I'll have to go back to this instruction and fill that specific address with the end of the body of the while loop at some point. This is something that I will have to do. So, but to do that, how I'm going to be doing that? So let me save. How I'm going to call that? How I'm going to call that condition jump. Right, so condition jump, something like that. I'm not really sure how to call that, but whatever. All right, and after that, I just need to start parsing a body. Yet again, believe it or not, I just need to start parsing a body. I need to start parsing a statement. We don't really have a way to parse a statement, unfortunately, which is rather interesting. So, because parsing a statement is just like parsing a function body, believe it or not. It's just like parsing a function body. Yeah, now we need to reorganize everything that we're doing here, which is rather interesting. Okay, so I think I have a hack that I would like to employ in here so I don't have to reorganize this entire function, right? So what we can do, we can explicitly expect open curly brace. We can explicitly expect open curly brace at the beginning, which is not a correct B syntax, actually. It is not a correct B syntax. Because what you can do, you can just have a statement. This disallows you to have statements that looks like this, where while true and just like print f something. This disallows you to do these kind of things. But again, to allow you to do these kind of things, I need to like greatly reorganize this code, which I don't really want to do right now. Maybe later. Right, so here we expect open parent, and then we call compile function body yet again, which expects that you already sort of pre-parsed this kind of thing in here. So it forces you to always have curly braces in while loops, which I suppose is something that the Rust developers would be happy about, but this is not a correct B syntax, right? So this is not a correct B syntax. So because of that, I'm going to put it to do in here, right? So something like this. Factor out parsing statements. Parse the body of the while loop as a statement, not as another function body. So that's kind of important, I think. So here's the input path, and then this is the variables. This is the auto variables and stuff like that, and we pass another function body again, so it generates a nested one, and also the data. So here we're collecting the data section and stuff like that. So compile function body, it returns a boolean, so that means if it's not true, we have to return false in here. And by the way, here we have to have false instead of 1. Okay, so that's pretty cool. That is pretty cool. So that compile the function and so on and so forth. And here we need to emit an instruction that will unconditionally jump back to the begin address. That's what we have to do, unconditionally jump back. So let's go ahead and do that. So do I append func body, and then jump address is going to be the begin, and it doesn't really accept anything else, right? So it's just like a address begin. So that's it. And here we have an instruction into which this instruction have to jump, right? So it's basically an end. It is basically an end, like this. So now we have to set end as an address of this instruction, but we can't really like move it in here and set end, because end in here is not valid. It is only valid after you compiled the body of the while loop and edit this instruction. Only then that end is valid. So that means we have to backpatch this instruction. So that's what we have to do. We have to backpatch it. Yep. So interestingly, I wonder how it would be easier to do that. Yeah, gotta parse the body before knows it ends. But it's not about parsing. We're not parsing here. We're compiling it. Not gotta parse it. Gotta compile it first. So we need to generate instructions, literally generate instructions, before we know to which instruction we jump. It's not parsing. That's already beyond parsing. We already passed parsing a long time ago. We're generating shit. Yeah, so we're compiling it. It's a single pass. Yeah, exactly. It's a single pass. So because it's a B compiler, it's a predecessor to C. Yeah. So what's the easiest way to do? And this is, by the way, why we're saving the conditional jump right in here. So then we can go take a function body, right? So we need to take its items, and items is a pointer. So that means we have to add the conditional jump. And in here, it's kind of stupid, I know that, but it's crust, right? So we have to, I think the easiest way for me is to just like literally assign it like that. Right, I think that's the easiest way for me to do. Yeah, so parse the body of the while as a statement, not as, yeah, so this is it to do. And yeah, that's it, I think. So we already, as already said, used both of the instruction unconditional jump and conditional jump. Right, so and in here, effectively, that's it. Essentially, then, so this is the open parent, but the open parent has to go after compiling the expression, right? So it goes somewhere here. Yeah, there we go. So here's the while loop. We expect open parent. We save where the entire while loop begins, right? So might as well actually put it in here. So this is in here. So expect open parent, compile an expression, which is the condition, then obviously expect close parent, save where we have to, where we perform conditional jump and add the conditional jump, right? So we're sort of like putting a stub on this instruction in here. Then we opening the curly brace and compiling the function body, which is not particularly correct, right? So, but I like doing it correct requires restructuring the code. Don't want to do that. So after we compile the body, right? After we compile the body, we do conditional jump back to the beginning, right? So because it must loop, right? And after that, we're going back to this instruction that has to move after this unconditional jump, and we sort of like backpatching it, right? So with already known correct address. Yeah, compile block body or something. I would rather call this kind of thing not really function body, but rather compile statement, because statement could be one single thing with semicolon or a bunch of things in a curly braces, right? So like it's not correct, but again, it requires too much refactoring that I don't want to do right now. Right, and I think that's it. So logically, this is how I would compile while loop. Right, so this is basically a sketch of the idea. It's not a complete sketch because maybe it contains compilation errors, and it definitely doesn't contain implementations of jump if not and jump, right? It doesn't contain any of this implementation. So this is a rough sketch. So now I have to solidify it by doing the, you know, the compiler assisted refactoring. So let's go ahead and do it. All right, so obviously it doesn't work. Right, so it wants the prefixes for all of these things, of course, because it's Rust. Okay, so len, it's actually not len, it's count. That's true, it's a dynamic array. It's my custom homegrown dynamic array. So it doesn't have len methods or anything, but I mean, it's just a reflex, it happens. So here's the mutable. I don't have to pass it as a mutable because it's already a pointer. Okay, yeah. I forgot the dot, All right, so what else do we have in here? Now we're freaking talking. So now we're talking about generation of all of these instructions. So let's put OP, jump, jump. If not, I'm gonna ignore everything in here. I'm gonna just put to do. And also for the jump, right? None of them are implemented. I just want this thing to compile. All right, so this is a JavaScript. Okay, so for the JavaScript, I'm gonna do the same, honestly, right? I don't want to really bother with this kind of stuff right now. This one is going to be to do like so, and this is jump. Anything else? And this is intermediate representation. For intermediate representation, I can just like generate them because I want to be able to see them. So OP, func, not really Funcall, jump. If not, jump. If not, it's an address and argument, right? So this is more of a condition, right? So this is more of a condition, and I can just go ahead and, you know, print them somehow. So it's going to be append, sb append output c. It has to be a macro, obviously. 4. Can you see Scheisse in this list? I think you should be able to. So jump, if not. So in here, we just have the address and the argument. This has to be a new line. So the address is just a number, if I'm not mistaken. So that means it has to be ZU. The argument is more interesting because I think, yeah, so we just do it through dump argument. Okay, so that's really dumb, but it is what it is. So that means I have to do it like this. Can you see? Oh, yeah, you can see what I'm doing. Oh boy, where is my sway? So I have to do it like this, maybe even, yeah, something like this. So this is address. So then I have to finish printing output. Almost there. And I think that's it. Yeah, so here's an address, then argument, and then this thing. Okay, that's very cool. It's kind of stupid, but I mean, sure. So jump, and this one only contains an address, which is much easier. All right, so it's just a jump, then this new line and address. Okay, what else do we have? All right, expected the, ooh, motherfucker compiled. Motherfucker just compiled. I'm not even joking, right? So it now fails at the next feature that we need to implement. Right. But if I try to, okay, so now it failed at, that's very cool. It failed at x86-64 generation. So now we need to generate x86-64 for this stuff. Okay, but I want to see how it looks like at least, right? So let's actually set a target to intermediate representation. All right, I think it's just like with a single dash. It's the wrong place. All right, permission denied. Well, I mean, I didn't want to run it, Brovsky. Yeah, okay. So let's take a look at the FIP. Cool. So jump. So it's pretty cool. So here's the binop less. This is the problem, right? So we're doing addresses, but we don't know where the fuck they're located. So now, as we do intermediate representation, we have to actually enumerate all of these addresses here. We have to enumerate them. I have to do that. Okay, let's quickly do that. So yes. So generate IR. We don't even have anywhere in here. Where is that? Ooh. So jump if not. Yeah, here it is. So for each individual, yeah, so we know its index, we can actually append it somewhere here. So append output, and let's just put it like that. So it's gonna be ZU. Might as well just use something like 08. So it looks like an address, or maybe even with the spaces, right? So we can use it as spaces. And just like use I, because I is the address in here. So might as well put, yeah, let's not put anything in here. Okay, let's fucking go. So here's the fib, and I'm gonna do something like that. Look at that! Isn't that a poggers, my friend? Isn't that a poggers? So, okay, so here's the 5. It jumps to 5, where it allocates a new variable, which is kind of dangerous, right? So we're leaking temporary variables, but that's fine. So the stack is growing. Then does the comparison, and then what it does, it unconditionally jumps into 14, which is behind this unconditional jump in here. Look at that. This entire thing, 14 jumps here. Right, then it does the body, then it jumps back to 5, which does the comparison. Right, then does again. So this is a while loop. Look at that. This is a while loop. So it works. It leaks the temporary variables, but that's expected. That's actually expected. So we have a separate issue for that. We don't generate x86-64 for this thing yet, but it shouldn't be that difficult. So the only problem here is that, like, what's the labels though? We can do a Porth trick where for each individual instruction in x86-64 we always generate a label. Yeah, so we can have a Stack Overflow on while loop. It's not a fucking joke. Yeah, so we can actually have that. This is a limitation of our current compiler, but I mean, again, not everything at once, right? So not everything at once. I have a to-do for that. It's a known issue. I'll fix it eventually. Just like, it's like I need to focus on things, on specific things. So what if at compile time you totally send the AR through stdin so you don't leak them? What the fuck are you even talking about? That's why I didn't read chat. Anyway, so we need to generate x86-64. x86-64. So we're gonna be doing GPT message exactly. doesn't even make any fucking sense. Anyway, like there's no even way to answer to that. It's absolutely meaningless. So how are we gonna be doing that? So let's actually go ahead and just try to compile this x86-64. Okay, not implemented. So yes, for now, by the way, we can generate some scheisse. What if we literally just say sb append output c to do jump if not? That's an interesting way of doing that. I think. Okay, so as you can see here are the to-dos. So it generated the body and stuff like that. This is a really nice way of actually developing it, right? So for things that are not implemented, just generate like to do and let the assembly fail, right? So let the assembly fail. So again, we can do a trick that I did in Porth, and I don't really like this trick because it works and it makes me super lazy and not want to implement a proper solution. But I'm gonna employ it nonetheless, so fuck that. So let's go ahead. Append output C, and like I literally just say like OP ZU like this, and it's just like I. And I'm gonna just do something like that. And yeah. So all right, let's actually make it a relative addresses actually. Let's make it relative address. Let's revert. So it's with the dots and stuff like that. Look at that. You see? You see it? So now it's actually super easy to know where to jump. Yeah. So just go ahead and generate some things. So, well, I mean, with the conditional jump, it's a little bit annoying. With unconditional jump, it's super easy. So let's actually first implement the unconditional jump. So unconditional jump is down there. So here it is. We should be able to very easily implement it. Okay, so unconditional, it accepts the address, which means that we just do GMP, OP, ZU, and that's the address that we put in here. So let's do that. And it didn't like something because it's an address. So, and if I open that stuff, look at that, it just jumped to OP5, and OP5 is here, right? And as you can see, it it does this allocate temporary variable, so it like increments the stack every fucking iteration. Bro, like this is like a tail recursion, but the opposite. Right, it's a tail recursive the tail call optimization, but opposite. It's iterative process that overflows your stack. Non-tail recursion, right? So the tail call optimization is the point is that you have a recursion that doesn't overflow the stack. Here we have iteration that does overflow the stack. It's the worst of both worlds. Holy fuck, I love it. I actually kind of like it. I really freaking like it. It's fucking while loop that overflows your stack. Damn, that is so fucking funny. Speaking of programmer's joke, a real programmer's joke is none of that semicolon shit. This is the real fucking programming joke. A while loop that overflows your stack. That is actually fucking funny. Okay, how are we going to be doing a conditional jump? Conditional jump. So here we obviously have an address. And funny thing is that the conditional jump jumps to label that doesn't exist, right? So that's kind of the problem here. But I mean, it's not that difficult to fix. So here is the address, and we also have arg. And arg basically can be located in any of these things. I suppose the one thing we can do with the arg, right? We can just take an arg and just load this motherflipper into rex. I should stop doing that. It's stupid, but anyway. So move rec. Don't fucking do that. So here's the rex, and yeah. So depending on where it's located, we're just loading it into rex. Yeah, so we have to probably check if it's 0 or not, right? So, and that's relatively easy, I think. SB append output C, we can do zor rex. I mean, I said rex 2 times, right? So because it's basically, as already said, it's a zor rex to rex. One more time, rex. I'm sorry. So we do that, and by the way, that will set the 0 flag. That will set the 0 flags if rex is 0. Do I remember correctly? Yeah, I think so. Which enables us then to JZ, right, jump F0 to the OP of the address. Look at that. Will that work? I think that will work. But it's just like we're jumping to a label that doesn't exist, but it's actually very easy to edit. JZ, yeah, exactly, JZ. Okay, let's give it a try. So, yeah, again, you're jumping to something that doesn't exist, but that's fine. We can make it exist. Right, so let me see. Okay, so there's not a single to do, right? Not a single to do. And in here, so JZ, you're trying to jump to OP14, but it doesn't exist because the maximum is OP this one. Honestly, I thought that I need to prefix it with something, but I actually don't, because it's a local label, which is automatically prefixed with this one anyway, so I don't have to worry about this kind of stuff. So essentially, you can just like add additional label after the generation. So somewhere here, well, I mean, you have to do it here, where the size of the label is actually body length, right? So it's this one, and it compiles. So, yep, that works, I guess. It will be kind of interesting to test it properly. All right, so we can't compile this example yet because we don't support several arguments, like the arity of 2. But we can maybe craft a different example in here. Right, so if I just enable this thing, it is not going to compile, right? Because you can only do this kind of stuff, right? So you can only pass one argument to function call. Yeah, because it requires additional implementation. One thing we can do, let's do a sequence example, sequence B. All right, so in here, we're gonna be actually using only put char, extern put char. Let's allocate variable a, and additionally, initially it's equal to 0. While a is less than 10, what we're going to be doing is put char a plus 0. What was the 0? 43, 48. I think it was 48. Yeah. I already forgot. I apologize. 48. Okay, so it was 48. Then we're going to put char new line. I think new line is 10. Yep, it is new line. And then we can do a plus 1. So we should be able to do these kind of simple things already. So let's give it a try. Okay, so I'm gonna just compile it. So this is sec. Aha. Well, I forgot. Freaking Rust. Compile. Rust damaged my brain. I'm sorry about that. So ASM, what do we have in here? So that looks okay. That looks okay. So we're jumping back into O3, where we obviously leak in variables, and then we do JZ, which is OP14. It's actually kind of the same amount of instruction here, surprisingly. And what's funny is that it also compiles, right? So here's the final executable. I haven't run it yet, but I want to do is the following thing. I want to do target IR. I want to take a look at the IR. Yeah, it's this one. Let's take a look at the example sec. Here's the IR. Yep, that looks all right. That looks all right. By the way, I'm sure leaking the variable will invalidate some of the variable indices in here. No, it won't. Bro, leaking the memory won't invalidate because we're accessing the variables not from RSP, from the top of the stack, but from the stack base. We're basically going to be leaking the variables, and we're only going to be using the variables that are needed. Okay, here's the thing. We can do a very cool freaking thing. We can get rid of these auto allocs all over the place. We can get rid of all of that stuff. What we can do, during the compilation, as we traverse in the syntax tree, which we don't build, we only traversing it by basically parsing it and automatically generating, we can figure out what is the maximum value of the temporary variables that we will ever need. Just basically do the max, right? As you go basically DFS in a tree, you basically do the depth. What is the deepest path of that tree that you get? You get that deepest path and you pre-allocate only this amount of variables. Yeah, pre-allocate everything up front, right? So a single auto alloc, right? And then deallocate everything at the end of this entire thing. And you don't even have to ever worry about the subscopes and stuff like that. Just like pre-reserve. And yeah, this is a very base solution, honestly. This is a very base solution. just like C would do it. Does C do it like that? But I mean, there's a lot of optimizations you can do. Like some of the like temporary variables probably not needed. You can get rid of them. By the way, we're probably gonna have an SSA stream at some point. I really want to get into SSA. Well, I mean, it's freaking IR. Intermediate representation. IR. Did you guys know that IR actually stands for Iran? Yeah, that's what it stands for. Iranians invented intermediate representation. That's what it's called like that. So I want to do SSA. And SSA is actually kind of cool for getting rid of like redundant variables and stuff like that. Because it allows you to build this graph of assignment that you can then traverse and prune, getting rid of the redundant variables and stuff like that. With this Arabic chairs, this was Arabic script, but I suspect it was actually Farsi, and Farsi is not an Arabic language. It just uses Arabic script. Because like I put IR, and IR is the country code of Iran. They don't speak Arabic, they speak Farsi, but it uses Arabic script. It's kind of similar to Mongolian language, right? So Mongolian language is not a Slavic language, but it uses Cyrillic nonetheless. And not all Slavic languages, by the way, use Cyrillic. So it's kind of a mess, right? So, it's kind of a mess. But anyways. So there is a good chance that this was not Arabic, but actually Farsi. There's some ways to distinguish them, but if you don't speak either of the languages, I think you won't be able to do that. Right, it's just the same. If you don't speak neither Russian nor Ukrainian, you won't be able to distinguish them, right? So even though if you know the clues to look for, you probably won't be able to do that outright. Oh, there is also a very interesting situation with the Tajik language, yeah. It's basically Farsi, but with Cyrillic alphabet, yeah. So Tajik language is Farsi with Cyrillic, and for Iranian, like Persian language is Farsi with Arabic script. Okay. So, but it's basically the same. I suspect maybe there are some differences in pronunciation and maybe some differences in vocabulary, but that's kind of normal when the languages are separated like that for a long amount of time. After all, there is a difference between Spanish in Spain and Spanish in Mexico, right? Slavs and Persians are somehow related. Well, I mean, we're kind of neighbors, so more or less, we're kind of close to each other. So wouldn't say we're related, but we have kind of a shared history, I guess. Anyways, let me see. Okay, what I want to do, I think the time has come to freaking call this thing and confirm that this entire stuff works. Okay, so example. Fuck. Okay, it didn't work. So even though, yeah, all right. So that's kind of weird. So what exactly happened? Let's try to troubleshoot that. Ooh, this is actually kind of cool. Tajik to Persian seems like old Farsi. We couldn't understand each other. This is very freaking close to how Russians see Ukrainian language as well. Because a lot of words and a lot of constructions kind of feel ancient to Russians, but in Ukrainian they're totally normal. It's kind of interesting. So anyways, but it's only like feeling, right? So it's just like it only feels ancient because in our language we haven't used it for a long time, right? So if we used it more regularly, it didn't feel ancient. Do you understand Ukrainian? Yes, I do understand Ukrainian. All right. So what's going on? I feel like I feel like we fucked up the conditional jump, chats. I have a feeling that we fucked up a conditional jump. So I move this entire thing in here, right? I do XOR, right? I do the XOR, and if it's 0, I'm jumping to OP14. So XOR Rax is always 0. Oh, so I have to use CMP then. So how do I check? Yeah, test. Thank you. I fucked up in here. Okay, I fucked up in here. Thank you so much. I thought about the test, but I still did the XOR. Yeah, it has to be test. Fuck me, mates. Fuck me. Okay. All right, so absolute choding. Look at this. Absolute choding. While loop in a B compiler built from scratch. Like, for real, absolute choding, isn't it? It's so fucking cool. The fuck? You can't really go further than that, right? So because we can only print a single character in this specific example, right? So we can only print a single character. I mean, you can put 20 and it's not gonna look nice, right? So let me try to do that. So it's gonna be examples, examples sec. Yeah. Ooh. I mean, okay. So it's just like it went further in the ASCII table. So it just went further in like an ASCII table. Okay, that's fine. That's expected, kind of, sort of, kind of. And this is now that. All right, so let's go ahead and just add this as an example. I think that's pretty cool. So here's the sec B. And also I'm gonna go here and I'm going to do something like that. So this is the last thing that we need to implement, at least 2 arguments for function call. All right, so let's go ahead and do that. Save. So what did we implement? We implemented while loops. All right, so implement while loops. And let's actually do it like that. Boom. All right, and let's push that right into the repo. So yeah, the only thing that is left is arity, variable arity. If we take a look at the function call operation, the argument is basically option arg. I think, I have a feeling that the easiest way to add support of the variable arity is to just make it an array, right? And just follow the compilation errors, essentially. So that's basically the last thing that we need to do in here. Function call args. So on the level of the code generation, we still probably gonna introduce some sort of a limitation in how many arguments you can have, right? So because I don't remember Linux x86-64 ABI, but you're supposed to pass arguments to the registers, and if you ran out of registers, you have to put them on a stack. I don't really want to implement the whole logic like that right now. Right, so I think we're gonna just support 2 arguments, right? But I mean, we're gonna put the responsibility of figuring out how to pass the arguments to the code generation, right? So the parsing process is gonna just like take all of these things and just put them into the operation. Okay, technically this is already closer to AST, right? So you have an operand and you have, okay, so this is already kind of getting to AST, but it's not really AST. So it's not AST in a classical sense, right? I think. But anyway, so let's actually go through the compilation errors. Okay, here's the arguments, right? So here is the code generation responsible for the arguments and stuff like that. So here we have arguments. What we're supposed to do, we're supposed to probably iterate them. Let me think. So what's the second register in x86-64 Linux? First argument is RDI. The second one is, I don't remember. So what is that? RSI. Maybe it's RSI. So x86-64 Linux ABI registers for integers. Yeah. So, but I want to make sure. So the problem with this convention is that it's slightly different depending on function call and system call, right? So you should not use the registers for the system call for the function call integers. So there's a slight difference. What are registers preserving through? Well, I mean, this is not what I asked. Stupid Google. Stupid ass Google. All right. So this is not what I asked. That's so fucking dumb. And it put it as a first freaking result. Oh, anyway, I'm so sorry. I'm just so mad at Google. It's so goddamn fucking stupid. Like, it's intentionally so stupid to piss you off. Maybe to make you use their LLM garbage or whatever. I don't fucking know. All I need is a freaking list. And it's like impossible to find. Okay. So RD, it's probably RSI. Okay, so let's actually do something like, I don't freaking know. So registers, and it's gonna be something like so RDI and then RSI, right? And so if yeah, supported registers, if args len is greater than, we can even make it a const, by the way. So let's call it registers, and let's actually make it explicitly a constant to a slice of constant cchar. That's how we're going to be doing that. If registers length, if the amount of arguments is greater than that, this is straight up an error. What we can say in here is, okay, how can I say that? Too many function call arguments. We support only this, which is the register this thing, but well, I mean, we support only this, but this were provided. Is that a good way to do that? Maybe. All right. So this is what we get. So after that, what we have to do is just iterate like this. In 0 args len, and a single arg is essentially is args I. Okay, so we don't need that stuff. And because of that, we may be actually able to inline this entire thing. And now, look at this register stuff. We can replace all of that register stuff with some other things. So can I quickly do something like this? Oh my god, this is so... Using this macro is actually super satisfying. I really like this macro. So, and here, what we have to do, we have to replace it with s. All right, we're replacing it with s. So then later, we can do registers. I have to dereference this entire thing. I, like this. Can we align that stuff a little bit later so we can see all of that? Yeah. We might as well also put this stuff in here. So this is the current register, and just replace that stuff with reg. Look at that. So satisfying, honestly. It's just like automatically. Soon we're gonna have a support for the entirety of Linux x86 ABI. Anyway, so let's try to compile this entire thing. It doesn't compile because we haven't finished all of this stuff. So it is saying, this one is count, yeah, I know, I keep forgetting that this is not the Rust stuff. It's a count, it must be count. And here we also have to have a count. What else do we have? Okay. Cannot be dereferenced. Fuck. Okay, so it has to be something like items add. Yeah. And only then we dereference this entire thing. What is it saying now? Args. Ooh, this is, what is that? This is JavaScript shit. Okay, fuck JavaScript. I'm gonna implement JavaScript later, like I don't care about it. Okay, so function call, this is args. Ah, and what is that? This is, yeah, this is still JavaScript, right? So we have to be a little bit careful, but I mean, we can just do something like this. All right, what else? What else do we have in here? Well, freaking, okay, what do we have? Aha, all right, this one is interesting. This one is interesting. So it's a multiple of these things. It's a multiple of these things. And effectively, I think we can make it work. I think we can. So essentially, we always do that. Always do that. Remove this. And then always do that. Always do that. And we kind of similarly just do for each. I in args count. Well, from 0 to args count. And we just do something like this. So we always have to put comma space, and that means we can also put s in here. Well, I mean, it's not really s, it's just a dump arg, and that's it. Well, I mean, it's args items, add I and reference it. This, so that will work as well. Anything else? Args. Ooh, what the fuck? What the fuck is that? What the fuck is that? So this is a function call. I see you. We got to the parser. We modified the intermediate representation instruction to accept variable amount of arguments, and we went up there and we reached the parser. Now we need to figure out how to parse function calls with several arguments. Now we know how to generate the code with them, but how to parse. So it's kind of interesting. So some people start from the parser down to the generator, but sometimes it's easier to start from the generator up to the parser. So you can actually go up and down. Doesn't really matter from which side you start doing things. Okay, so here is the open parent, right? So, and we check that the function exists and stuff like that. So, and this one is rather interesting. So we look ahead and see if it's an open parent, a closed parent or not, whatever. And if it's not, we parse in this entire thing. So I suppose, so this is an arg. Instead of this stupid ass arg, what we have to do is args, which in fact is an array of args and it's initially zeroed. So it is emptied out. And funnily enough, we look ahead, and while this thing is not equal to close this stuff, we restore saved point, parse one argument, and I suppose we can just append, append that argument to here. And that's it. So that's how we do that. Wait. Well, I mean, we also have to expect comma, right? So one of the things we have to do, I feel like, okay, so get and expect. We can actually get and expect either parent or comma. Sandix, what's up? I haven't seen you in a while. How are you doing? How are you doing? How's your Oblivion playthrough going? Cheers, by the way. What do we need to do? Compile a Borg, exactly. This is true. It's kind of borked. We need to do get. All right, so we need to get this thing, which means we can get rid of this stuff. Then expect Klexes. Klexes. And if it's, we expect either that or that. This one is annoying, honestly. This one is annoying. So what we have to do is if yeah. If we didn't have to do comma, I think it would have been easier. If we didn't have to do comma, it would have been easier. Yeah. So what if we just always require, well, I mean, it's kind of stupid. So if L token, if it is equal to comma as schlong, that's totally fine. We just continue, right? We just continue. And we also have to accommodate for this kind of thing, I think. I think we have to accommodate for this kind of thing, but I'm not 100% sure. I feel like we need to, yeah, we need to have a special case for zero arity. Yeah, I think there should be a special case for zero arity. Right, so, and this case is going to be if this thing is not equal to this kind of stuff. We say we're restoring the saving, and while this thing, we just keep doing that. And we never have to save anything actually in here. Saving is not really necessary in here. Yeah, so if it's not equal to that, we just restore the saving, and while this token so here's the thing, I feel like this has to be a loop, just a loop, because now, right, so we're expecting close parent or comma, right, and if L token is close parent, we break out of this entire thing. Otherwise, if this thing is comma, we continue. If it's something else, it's unreachable. I think I figured it out. Chat, can you believe that? That's the way to go, I think. Right, so we look ahead. Does it, you know, is it open parent? If it's not, well, if it is, we just like parse it and so on and so forth. If it's not, we roll back and we start in this entire loop where we parse an expression, append it, look at the next thing. Is that a comma? Continue. Is that an open parent? Stop. Yeah, loop break. Yeah, I really like the loop break, honestly. Loop break, loop. It's going all right. It helps me relax a bit. Understandable. Oblivion is actually kind of cool game. I want to, yeah, I kind of want to play it again, honestly. I haven't played it in a while. So this one has to be if. Yeah. And actually, wait a second. Fuck. Not. Yeah. So this is not args, this is arg. And this is args. Yep, this is as schlong. As schlong compiled. So I think we finally have multiple function supports. We can try to test it. It's actually rather interesting because in printf example, I have this thing. And it didn't work before, but now it should, according to my calculations. So we can test all of that stuff on printf. It worked. Example, printf asm. So here we call printf. So RDI, dat14, RSI 69. So here is string, literal, and 69. So RDI, some pointer, RSI 69, call printf. So That's this call. So it generated correctly. It's a almost absolute charging moment, but we need to test it first, right? It's kind of a neat assembly. Look at that. It's a very neat assembly, and it corresponds to this code. It's a pretty reasonable assembly for this code, honestly. So yeah, so it's pretty straightforward. There you go. So you have some data in here. Here's each individual instruction, stuff like that. Not fully optimized, but there's nothing much to optimize here anyway, so it's fine. So you can do. Apparently, at least Phasm didn't complain. But to be honest, this is a compile time value anyway. Like, I mean, assembly time. Right, so it probably knows where data is located. It probably knows 14. Right, so we can just do this computation at compile time. So I don't think it's that difficult to do. So anyways, let's do that and then do examples, printf. And it printed hello world 69. If you take a look at the original thing in here, hello world 69. Okay, so now let's go back to Fibonacci, and enable this entire thing, right? Enable this entire thing, and let's do fib. Let's not run it yet. Let's not run it. Compiles. So take a look at the examples. Fib asm, right? So this is how the asm looks like. Not that much, right? 56 lines of code. And here's a little bit of a data, and that's basically the string literal for printf. Do we call printf anywhere in here? We do in fact call printf with one of the temporary variables and the string literals. This is a kind of tight assembly. This is a very tight assembly. I think like removing some of the labels would make it even cooler, but I kind of like these labels because they kind of separate each individual instruction. It would be kind of cool to also put a comment in here, just like I did with port, right? Okay. So let's compile it one more time, and let's maybe run it. So I'm gonna do example fib, absolute charging. So we spent 3 hours making Fibonacci numbers compile, and there you go. So isn't that absolute charging moment? I think it is absolute fucking charging moment. That was actually kind of cool. That was fun. So yeah. Absolute compiler. We can now do Fibonacci numbers. So we can do rule 110 at some point to prove that it's Turing complete, but I mean, I'm probably gonna do that off screen. But you can't see. I can't see this shit. I'm sorry. So, oh, see what? How does it look like? But anyways, so let's do you know, committee and potentially a pushy. Okay. So okay, support fun calls with a variable amount with a variable arity. So we have a bunch of garbage in here, but I don't think none of the garbage is important. All right, and I'm going to push that right into the repo. So I'm going to think about more different kind of examples, but I think what's important is that we have developed an infrastructure for adding more control flow, you know, constructions. So just like we can add while, we edit while, so that means it's relatively easy to add ifs, maybe to add for loops, and so on and so forth. Right, so we created an infrastructure for expanding this language further and further and further. So it's not that difficult to now add support for function calls with 3 arguments. You just have to extend the register list that we introduced. So registers. Maybe we should call them x86-64 registers and stuff like that. This is a pretty basic support for, you know, x86-65 ABI. What's funny is that theoretically we can try to call Raylib a little bit. Well, I mean, listen. What you can do is extern init window, right? And then in here, you can do init window, something like this. Hello from B. Right, and that probably that's the only thing you can do in here, honestly. I mean, why not? We can give it a try. So we can try to compile this entire thing, right? So I'm gonna try to do Raylib B. Too many arguments. Okay, RDI, RSI. I think this the last one RSX, right? So RDX. I mean, so what was that? Was it RDX? Chat, please help me. I think it was RDX. I think it was RDX. So let's actually put RDX in here. Yeah, RDX. Thank you so much. So now we have that. And okay, so that's pretty cool. It failed at linking. It failed at linking, but it generated assembly that looks like this already. Which means, so do I have a Raylib somewhere? Wait, yeah, here it is. That's the only Raylib. Okay, so let me rename this entire thing. Yes, I said. All right, so can I copy paste this thing and unpack? All right. So, which also means, how do we link this entire stuff in BRS? So I just use CC. Okay, that's understandable. So we also use NoPy, which is rather interesting. I wonder if there will be any problems with this stuff. So NoPy, O, okay, Raylib. So the input is going to be Raylib O, right? So we have O, and I'm going to link with lib Raylib A. And in here, I have to do Raylib 5 lib. So, okay. It also wants to have math. You probably can't see that, but I need to link with math. And we acquired an executable. And if I try to run Raylib, you saw a window, and here's the log. Hello. It didn't freaking create, but I suppose it created the screen size 800 by 600, and this is basically a compiled program from here. So I mean, theoretically, we can already do Raylib from B compiler. We probably need to enable accepting linker flags, because one of the things I want to be able to do, honestly, is I want to be able to just pass all of that stuff through the B compiler. Didn't he add 2 arguments? Well, I mean, it's very easy to add 3. Right, look at that. Look at that. Look at that. Look at that. So, Raylib speedrun and B confirmed. Yep. I can't really do more in here, but maybe can I? Wait. So can I do, well, I can't return results from function calls, right? So I can't do, well, window should close, but I mean, begin drawing and drawing. So I can just like emit, you know, checking for window, clear background, and here we have to supply the color. Let's actually do the following thing. So FF0000FF. So this is the number that we need to pass to clear background. So let me do B. Okay. So as you can see, well, I mean, begin drawing. Okay. So we need to declare all of these variables, begin drawing, and also end drawing. So we forward declared all of these functions in here. All right. It compiled, but I mean, didn't compile. Clear background as well. Clear background. Okay, but it didn't link. But now, let's link all of that. And here's your Raylib application. Yeah, we have to do that in a loop. Oh, by the way, we're gonna have a Stack Overflow, chat. We're gonna have a Stack Overflow. Right, so we can do stuff like this. Yeah. There we go. That. And now if I try to link, It doesn't Stack Overflow. Ah, bro. Who can tell me why the application doesn't crash with Stack Overflow? Who can tell me? Who's smart enough? Why doesn't? Because we are subtracting RSP, but we never read outside of the stack. The RSP decreasing, but we don't compute the addresses of the local variable relative to RSP. We compute it relative to RBP. Still kind of weird, because we call functions. So we call functions with fucked up RSP. So that means it should crash at some point when it goes into Raylib, but it doesn't. This works absolutely accidentally. I have no idea how. And by the way, it's impossible to close it. It is absolutely impossible to close this entire thing because we don't check Windows should close. But we can probably send a kills. Yeah, okay. Interrupt actually works. Interrupt actually works. So it fucks up RSP, but it still works accidentally. But I mean, there you go. This is more or less like a real Raylib example in B. So this is memory. Well, B is not a memory safe language, that's for sure. It's probably even more memory unsafe than C. I think the stack is dead after you call. Well, I think stack is dead, but it's kind of weird that it still works. It's kind of weird that it still works. So can you show the while? Okay, sure. So let's take a look at Raylib asm. So here's the assembly. So yeah, this is literally what we do. We just like move one to rex, test, and then jump over if it's 0. So, and it just like goes to the end in here, as you can see. So that's basically the while loop. And in here we call begin drawing. Then we pass this red color to clear background. Then end drawing and jumping back to 5, where we do another check. And so on and so forth. So, oh wait, we never allocate anything in the stack. This is because just using one literal never needs okay. So it still works accidentally, but I mean it works accidentally at compile time, not runtime. Okay, so that's all right. So thank you for asking it. So didn't expect that. It's kind of surprising. All right, that's cool. So we can theoretically make it part of the examples. But again, it would be kind of nice if the B compiler just passed the linker flags to CC. Happy accident, yeah, it's literally happy accident. I didn't expect that. It's kind of funny. I really like the way I generate assembly in here. The generated assembly, by the way, is much more readable than the generated assembly of Porth. Porth generates absolute fucking garbage, honestly. This one, at least it's readable, right? So I think I'm like doing code generation in B better than I do it in Porth. So this one is at least readable. Yeah, still going. Yeah, it's already 3 hours. How difficult it is to pass the linker flags in BRS? How difficult? So here's... I don't freaking know. We may introduce additional flags in here. We're using flag library, which makes it kind of difficult to pass flags. So it's a whole different session. But I can add a to-do in here. Pass user flags to the linker. I think this is a very important feature. Yeah, being able to pass user flag to the linker. It will enable a lot of things. And so I'm gonna probably move raylib.b into here. And I'm gonna commit. It's not really buildable easily, right? So, but at least after some to-dos, we'll be able to maybe document how to build the Raylib example. Let's say outline a simple Raylib example. I'm gonna push that right into the repo. Okay, so I think we've done a pretty good job today, right? So we made Fibonacci numbers work. Let me try to maybe build them. Fib. It's kind of difficult to find. Just a second. Fib. Another fib. How to compile them? For example, fib. Made the Fibonacci numbers work. Also added semi-support for Raylib, right? So this is a semi-support for Raylib, not a full support, but semi. Right, so, and yeah, that enables me to add more interesting examples to the language. And the more interesting examples I have, the more interesting it is to port all of these examples to different platforms, for example, ARM, and just see how all of these examples work on, for example, mobile phone. I also plan in the future to add MIPS support, because I think somewhere I have a router that uses MIPS. And imagine like having a program that works on your main machine. You can make it work on your mobile phone. You can make it work on your router. You can make it work anywhere, right? Just like take a piece of hardware, look what kind of architecture it uses, port that example there, and it works there. So, and if you can control the entirety of the compiler, it's actually super easy. I think it's a kind of a fun exercise. But yeah, so I guess that's it for today. Thanks everyone who's watching me right now. I really appreciate that. So thank you, Lily Antia. I think I already said it. Thank you, Super Ketchup76 for Twitch Prime. And I see you all on the next recreation programming session with Mr. Azuzin. I love you all. Mwah.